Hello, good evening, everybody. Okay, I hope that everybody is fine. Now the temperature is considered very high in Malaysia, so please take care. For those of you who is not familiar or with very high temperature, so please do take care of yourself. Right, we have completed AS, right? Atomic absorption. The name is absorption spectroscopy. The machine is known as atomic absorption spectrometer. Yeah. So the one that we are going to discuss today is atomic emission, AES. So before we can discuss atomic emission, I need to highlight what are the difference between atomic absorption and atomic emission. Okay, of course, we have discussed during our first lecture how absorption and emission occur. That one I'm not going to discuss back. The electron excitation, where it absorbs energy, and then it relaxes back, emitting certain energy as well. Yeah. So those are during our first lecture. All right. So AAS absorption. Okay. What is the biggest difference? Of course, is it utilized absorption. It utilized absorption spectrum for the analysis. Yeah. For the analysis in terms of quantitative as well as qualitative. Yeah. So this one, if you remember that this is the light source. Sorry. So this is the light source of atomic absorption. Okay. And then that light source, hollow cathode lamp, will produce emission spectrum. Okay. And that emission spectrum bombarded the sample. Okay, so this emission spectrum should be the correct one for the sample that we want to analyze. Okay, for example, if we want to analyze plumber metal, then we should have a light source, okay, that will provide the correct emission light spectrum to analyze plumber. Okay. All right. So this one is what we have discussed. So this is where the metal that will receive the emission from the hollow cathode lamp. Okay. This is where the sample will receive and will be excited. And you're going to have the absorption spectrum. Okay. So this one. So this is the absorption spectrum. So based on the absorption spectrum, okay, this one, okay, it will be analyzed quantitatively, okay, so that you can get the concentration of plumbum just now. So by looking at this, because AAS depends on absorption, okay, you can see that it is suitable only for mostly single element analysis. Okay, so if you have a mixture in one sample, then you have difficulty in identifying a different or multi elements in a single sample. So even though AAS is cheap, okay, unfortunately, it's not that robust. Okay, you have to like isolate other metals first, okay, or remove them, and then identify using AAS, okay, because usually it's suitable for single element only, single metal, right? So that's the disadvantages of using AAS. So for today, we are going to discuss AES. Yeah? So the name is atomic emission spectroscopy. Okay, right? Or the machine is known as atomic emission spectrometer. The machine is known as spectrometer. The technique is known as spectroscopy. So please be aware on the usage of the word spectroscopy and spectrometer. Yeah, we have actually, it does not differ that much from atomic absorption. Okay, because it's based on excitation of the atom, the excitation of the electron, and when it goes down the orbital, okay, it will emit a series of spectrum, yeah, emission spectrum, spectral lines. Yeah? So those are the basis of how it is detected. But probably we can discuss in terms of the changes. There are differences of light source, yeah, in the instrumentations of AES. Yeah? So as I mentioned before, AES is much more robust, means that it can do multi-element analysis. So we can see from the steps AES, okay, you can see it's almost similar to AES. You have to prepare the samples, aerosolize, okay. Still you need to do desolvation, remove any water, and then atomization. But in AES, usually atomization and excitation occur in one go. So if you remember AES, you have the light that emit emission where it is received by the sample, and the sample will be atomized in the flame gas or flame, what do you call that? Okay, so it is called flame, flame AES radiation source. Okay, so for AES, usually we do not need the radiation source. We can do the things at one go on flame excitation in one set. Yeah, so I will show you later. All right. So this one almost similar. You have to aerosolize, desolvation, do some sample pretreatment, and we will discuss this and detection of the emission lines. So for emission spectrum, emission spectroscopy, we are focusing on emission lines. Whereas for atomic absorption spectroscopy, we are focusing on absorption spectrum. Okay, right. So this one is determination of elemental composition. So I think this is quite common, where you supposed to, if you want to analyze elements, yeah, especially metal elements, okay. AES also can do some organic analysis. AES, we know that it can do metal analysis, and AES as well is known for metal analysis, but it can also analyze some organic compound. But it is not really common. So the theory, okay, this one we passed this. We have passed this, and then we have discussed this in detail in lecture 1. So you can see basically the components of AES are similar to AES. The sample has to be atomized, dissolved, okay, and you have a monochromator as well as detector, and of course the display unit. Okay, so this one is similar. But you can see that this part, okay, so it's not that complicated like AAS, whereas because AAS requires a specific cathode lamp for a specific element. But for emission spectrometer, okay, you can do a multi-element analysis, okay, provided that you have a good atomizer system. Okay, so the functions of AES are this is the source. Okay, for sample vaporization, okay, this one requires this excitation, dissociation, and excitation. So the ideal excitation source will allow the excitation of all lines of interest. Okay, I will show you later what does it mean by lines of interest, because emission spectrum, usually we work with multiple lines of emission spectrum, whereas for absorption, we usually use a single spectrum, single absorption spectrum. So that's why emission spectrums can analyze multiple elements, whereas AS usually is single elements. Okay, right? If you look at here, so this is atomizer excitation source. Okay, so the cheaper one, flame, just like what is being used in AAS. And this is, of course, a bit more expensive, inductively coupled plasma. So the function of this atomizer excitation source is the same like we have discussed in AAS. So there are also others, microwave and electric arc. So this one differs. You can see that it provides different range of temperature. Okay, and you if you can buy if you have money, then it's good to buy this one, ICP AES. So ICP is the atomizer as well as the excitation source, 2-in-1. So you don't need extra like hollow cathode lamp to provide the excitation source. So if we look at here, right, mechanism of atomization process is the how the sample is introduced through the atomizer and excitation source. So that depends on the setup. Okay, sometimes you have like auto samplers. Okay, sometimes you have the capillary tube. Okay, so remember that the video that we watched last lecture, so they use capillary tube. So that one is various types. Okay, but the one that we are interested in, because these are the one when we talk about AES, usually we use ICP AES. Yeah, so we are interested in how ICP works. Yeah, ICP, remember, is the atomizer as well as the excitation sources. Okay, these one are all similar. The one that we have discussed in AAS, the function of monochromator and the detector is almost similar. You can see that it is using photomultiplier tube detector, PMT, so it's similar with AAS, right? So this is what we are interested in, inductively coupled plasma. So remember, this is the atomizer plus the excitation source. Excitation source. Okay. So the pictures, okay, it differs, depends on the brand, so the model. So it does not have to be like this. It can look it can have different looks as well. All right, so let us look at the picture of here. So you can see, okay, we need to have nebulizer. Okay, nebulizer is to provide, to change or to convert the samples into aerosols, small droplets. So that one is, it's not really a big issue. If the nebulizer is working fine, then your samples will be aerosolized, okay, before it can be converted into gases as well as atom. Okay, so nebulizers, of course, will be in the part of the ICP. Yeah? So the one that we want to discuss is plasma. Okay. Okay, this one, right? So this is what we call as the heart of inductively coupled plasma. Okay, so it's very technical. Okay, you can see here. This is where the use of argon. Okay, mostly we have to use argon. And then you can see that the argon moves here. So we have a combination of radio frequency, also magnetic field, okay, all right, to produce the plasma. Okay, so the plasma is when the argon, okay, is converted into ion. Okay, so we have this ion, okay, ionized argon is producing plasma. So in this case, plasma is not like your plasma in your blood. Plasma is a heat of wave. A wave of heat. It's a wave of heat, a very strong, high temperature region, okay, produced by plasma. So plasma is produced by argon ion. Yeah. So this is what we call as the torch. Okay. So you can see the argon gas, and then when you have a combination of radio frequency and also what we call as magnetic field. Yeah. Okay, that will generate the argon plus or argon ions, and these argon ions will generate a high temperature area, okay, high energy temperature area called plasma. Yeah. Okay. So this plasma, okay, you can see here the setup. So argon comes from here. The sample means that the sample that you wish to analyze that have multi-elements whatsoever, it goes together. And this plasma is the one that excites the metals in the sample, and you're gonna have emission spectrum. Sorry. Okay, so this is how inductively coupled plasma, okay, ICP AES different with flame AES or flame AES. They are sometimes atomic emission spectrometer still using flame, okay, just like AES, but it's not that good. But of course, it is very much cheaper compared to using inductively coupled plasma excitation as well as atomizer in the system of AES. Okay, so one thing is the use of argon gas. Argon itself is very expensive. Yeah, so you can imagine the maintenance and the cost that you need to make sure to have in order to use ICP to do the analysis. Yeah, but of course it is much more simpler and easier because it can do multi elements at one time. And you can see that it is also very sensitive. Ultra trace means that very low concentration. Yeah. Okay. Right. So this is the one that I want to convey to you, is on the use of inductively coupled plasma. So the rest are similar. Okay, aerosol, as I mentioned, aerosolized, dissolution, atomization, and excitation occurs in the plasma. Okay, both process happen in the plasma. Okay, you can see. Okay, and we want it to be atom. Okay, but sometimes, of course, we have these ionic states as well. Okay, and how it is measured, how it is measured. So for atomic absorption spectroscopy, I did show just now the absorption spectrum, okay, a single spectrum for single analytes. But for emission spectrum, they base on multiple wavelength. Okay, they screen, they screen. If you can do that, is good, because you can at least, not you, but the machines can at least identify which lines is suitable to be analyzed quantitatively. So that's why they have what we call, radical, it's not radical, it's radial. Radial view and axial view. So is the way that the system or the machine looks at the emission spectrum. Okay, so I will show after this a YouTube video which actually give you a better idea of how radial view and axial view being viewed. So there are, of course, advantages or disadvantages. This one is advantages of radial view and axial view. Can run any metrics, less maintenance of torches, okay, more intensity. Okay, so this is how the emission is being viewed upon. Sometimes is more easier if you understand it, horizontal and vertical. Yeah. And the issue of interferences, okay, just similar to AAS as well, atomic absorption spectroscopy as well. You're gonna have like spectral overlapped, okay, spectral line, and usually this is not really, okay, I'm going to show you, okay, this is an example of the overlapping of the spectral line. Okay, so this is overlapping of plutonium and calcium. Okay, and this is overlapping of plutonium and aluminium. But this one you do not need to worry, because the manufacturers, they have the software, so you don't have to think about the spectral interference. So it's not really common. Yeah, now they have a good system. So these are possibilities. Okay, these are, for example, if you are doing detection for calcium, so these are the elements that might interfere in terms of overlapping of spectral overlap. Yeah, and this is for aluminium. Okay, so these three elements might interfere, but as I mentioned, the new manufacturer now, they have set up a good software so that you don't have to think about the problem of spectral overlap. So the rest are similar, just like AAS. You have matrix effect. Okay, so if your sample is in blood, if your sample is in very dirty water, or your sample is in wastewater from industry, is very viscous, or it's very dirty and contains a lot of matrix, so you're going to have of course affecting the reading. So this is an example. This is the analytes. Okay, okay, and then you have extra peaks due to the matrix, okay. Of course, because matrix also absorb certain energies. If you want a clean spectrum, you have to do some pre-treatment, okay. We remember about separations, but sometimes we don't really want to, you know, extra work. We just want to introduce the sample straight away from whichever resources that you have. So you might end up with this kind of spectrum. Yeah. So this spectrum, of course, will affect the quantitative analysis, okay, because the system might view it, because you actually have to use a very good area, peak area to identify the concentration. But unfortunately, if you do not have a clean spectrum, then you might have not to say totally wrong reading, but might be the reading is not accurate. So how to overcome this problem? Of course, you can see that these are the one that we also discussed in EAS, atomic absorption, spectroscopy, dilution, because if your sample is too dirty, then you have to make dilute, filter. If it is too extreme, you have to do some separation first before introducing the samples to the system. Okay, matrix matching is standard addition method. We also discussed last lecture the standard addition method. So that is matrix matching. We have to use the matrix as part of the preparation of the standard solution, to construct calibration plot. We can also use internal standards. Okay, this is to all. You can buy internal standards. Okay, this is quite common. For example, if you want to run calcium, magnesium, so you need to buy internal standard for calcium, magnesium, and you add it to the standard solutions that you are preparing. Okay, so this also might be a bit costly because every time you have to buy the internal standard. So standard addition is the one that we had discussed before, where you use some matrix. Okay, the matrix of the sample is added to the standard solution. So we have discussed this in detail last lecture. Okay, so comparison with other spectroscopy technique. Okay, this one that we have discussed before, the atomic absorption spectroscopy, and the atomizer is using flame. Okay, so you can see that detection limit means that how low can the system detect the metal or any elements that you want to analyze. Of course, much lower is anticipated, okay, because sometimes you have to work with a very low concentration. So you can see now from here, of course, the AAS has a very low, not to say low, it has a higher detection limit, okay. ICP AES has lower, okay, means that ICP is much sensitive. This one, hydride generation, means that it is AES, but using a different kind of atomizer instead of flame. So it's more powerful. So you can see that with changes of atomizer, okay, the AES system can be converted into a much sensitive machines. Yeah. So you can see the best, of course, ICP-MS. I'm not going to discuss MS, but because MS stands for mass spec, mass spectrometer, which you have learned, I don't know, for those of you who has taken molecular spectroscopy, you have discussed about mass spec. So of course, this one is the most expensive, and of course much robust because it can analyze more organic compounds compared to just metal analysis. Yeah, this one interferences, okay, same as what we have discussed before. So I remember that I asked all of you, I think, to check on what is Zeeman effect. Yeah? Anyone can tell us what is Zeeman effect? In simple words. Anyone? You can just Google what is Zeeman effect. Omar? Anyone? Yeah, yeah. Yes, please.
Maybe
Yes, bro.
Uh-huh.
trace analysis for routine application.
Zeeman effect is?
Background correction for robust trace analysis.
Okay. Anyone else has any idea? Any other idea?
Zeeman effect is a magnetic field that can split the spectral line.
Okay, because I actually we cannot hear you clearly. Okay, so I hear magnetic field. Yes. Okay, Zeeman effect. Okay, because we are relying on the emission spectrum, right? Okay, so the emission spectrum, okay, spectra contain lines, right? Lines of the emission. And if there is a magnetic field, so there is a what we call, it will split the spectral line. So instead of you have a very good single line for a specific wavelength, you're gonna have like shadows of the lines, because it's gonna split the spectral line. So I think if it's good that if you can please read on the Zeeman background issue. Yeah. So this is an issue in any spectroscopic technique, the Zeeman. Okay, there's a lot of Zeeman effect, yeah, on spectroscopy technique. So it's good for you to know, but usually they have like all these manufacturers, they have this Zeeman background correction. Okay, so it's not to worry, of course, it's not to worry every day, but at least to understand what is Zeeman effect. Yeah. So you can see that from here, these are the technique just now that I have shown in terms of sensitivity, which one is more sensitive, which one is less sensitive. This one, of course, towards less sensitive. This one towards more sensitive. You can see the concentration is getting lower. So types of interferences, okay? Ionization, chemical, physical, the matrix effects, physical and chemical, molecular absorption, spectral, okay? So these are some of the examples of interferences in the spectroscopy techniques that listed here. And this is how to compensate, means how to solve the issues of these interferences. So be alert on this, but usually, as I mentioned, this is where the manufacturers compete with each other. The manufacturers will offer, okay, we have this, we have settled all this problem and so on. So this is where they compete in terms of technology to solve the issues of interferences. So if you look at in terms of cost, you can see that flame EAS, okay, has the cheapest. Of course, it's the cheapest, but you can see in terms of performance, ICP AES is much better, okay? And this one, because we are using X-ray, so sometimes we have difficulty to buy. You can see that it is highest, but it requires X-ray light source, X-ray source to operate, so it's not really preferred. But of course, you can see the performance is much better. So now, if you have money, then please buy this. So application-wise is similar. You can see commonly, these are some of the samples, okay? And these are commonly used techniques. You can see ICP OES. Okay, what's the difference between ICP OES and ICP AES? Anyone? AES stands for atomic emission spectroscopy. So what is OES stands for? Hamima, sure, I'm sure that she knows. It's optical, right?
Yeah, optical.
Optical emission spectroscopy. So what's the biggest difference when we say optical? The word O instead of A.
I think, yeah, it's the same instrument.
But using optical?
I'm not sure.
Okay. So it's good to check because I don't know, nowadays we are prone to use optical. I think I'm not really sure, but it is related to optical fiber. So please check. So I have attended before a briefing on that, but I'm not sure. So now if we look at the robustness, how robust, we can see that AS is not means that it is quite limited, okay? So the most robust is ICP OES and ICP MS. You can see that this is the indicator frequency of technique being used. Right. So if the rate means that it is frequently used, whereas white is less frequent. So we can see from the red color, it seems that AES is, of course, much robust technique to be used. So as I mentioned, if you have money, it's good to buy ICP, right? So let me share a video, okay, before we discuss on the tutorial session. Okay, just a moment.
Three main atomization, where we atomize our sample, converting it into gas phase atoms and ions. Excitation, where we provide sufficient energy to promote the valence electrons of an atom from the ground state to an excited state. Both atomizations and excitations can be achieved efficiently using ICP. And finally, relaxation, where the excited atoms relax back to the ground state, giving up their energy as photons. This is when the atomic emission occurs. Let's take a closer look at sodium atom as an example. Sodium has 1 valence electrons in the 3s orbitals. If we supply enough heat or electrical energy, we can promote the electrons from the ground state 3s orbitals to 3p, 4p, or 5p excited state orbitals. After a few nanoseconds, the excited atoms relax back to the ground state, giving up the energy as atomic emissions. As shown in this energy diagram here, the wavelength of the emitted light depends on the energy gap between the atomic orbitals, which is unique for every element in the periodic table. In this example, this wavelength of 589 nanometers is responsible for the yellow light we see in fireworks that contain sodium salts. Here are some examples of atomic emission spectra of different elements. As we can see here, one element can have a set of characteristics.
Okay, this is example. For example, you want to analyze helium and neon at the same time, right? So you're gonna have a spectral overlapping, okay? So spectral overlapping, of course, is not good for quantitative analysis. So instead of using these blue lines, you can focus on other lines. Okay, you can use other lines. For example, if helium and neon, you can use this green line. Okay, different wavelength. It is, of course, the difference is quite big. So the system can choose different lines, different wavelength to analyze. Instead of using the overlapping spectrum, we can choose. So this is the beauty of using emission spectrum or spectra to be analyzed for quantitative.
Emission wavelength. ICP-AES take advantage of the unique line spectrum of elements to identify and to quantify them. The ICP-AES instrument we'll be using in this experiment can analyze more than 70 elements in the periodic table with very low detection limit. Atomization and excitations can be using either flame or inductively coupled plasma. Then the next question would be, which of these atomization methods is better? The typical,
of course, these are the one that we have discussed. We have flame AS, flame AES, as well as ICP as the atomizer and the excitation source. Which one is better?
typical atomization temperature using flame is around 1,700 to 3,100 degrees Celsius, depending on the fuel and oxidant we use, while the atomization temperature using ICP is around 4,000 to 6,000 degrees Celsius. Flame atomizer are usually used in AES and AES, while ICPs are used in AES and mass spec. When it comes to AES, ICP atomizer is usually preferred over flame due to the much higher atomization temperature of ICP. But why is it so? This is because the emission intensity depends on Boltzmann distribution. According to Boltzmann
let's
distribution,
skip this.
the ratio between the population of the excited state and the population of the ground state.
Okay, let's skip this. I'm going to show you the other one.
Hey guys, Francis here. In this video, we are going to learn about what is ICP and how does it work. ICP stands for inductively coupled plasma. So the first question we should be asking is, what is plasma? A plasma is a conducting gaseous mixture containing a significant concentration of ions and electrons. Argon plasma is commonly used in ICP, where the principal conducting species are argon ion and electrons. So how do we generate argon plasma in ICP? Well, let's take a closer look at the instrumentation. This diagram here shows a typical setup of an ICP instrument, which consists of a sample introduction system and a plasma torch. First, let's take a look at the sample introduction system. In ICP, samples are introduced in a steady and continuous stream while an autosampler, The autosampler we will be using in this experiment can accommodate up to 60 samples at a time. A nebulizer then converts the liquid sample into an aerosol, which is a fine spray of droplets or mist. Then we have a spray chamber, which serves as a droplet-sized filter, where the larger droplets will be removed and drained, while the smaller droplets will be carried into the plasma torch.
Okay.
The ICP torch is made of 3 concentric quartz tubes.
Okay. So you can see that this is where the sample enter, the entrance of the sample, and this is where the argon gas will enter. Okay, this one goes
Which argon
the
gas
hardware.
flows through. The sample aerosol is introduced while the central tube. The tangential argon plasma support flow helps cool the inner walls of the central tube. The top of the outer tube is surrounded by a water-cooled induction coil, which is powered by a radio frequency generator. This will generate a fluctuating magnetic field. The ionization of the flowing argon is initiated by a spark from a Tesla coil. When the resulting ions and electrons flow through this region, they interact with the fluctuating magnetic field. This interaction causes the ions and the electrons within the coil to flow in a closed annular paths as shown here. The resistance of the ions and electrons to this flow of charge causes ohmic heating of the plasma. So this is how ICP works. Typically, modern ICP instruments offer 2 different viewing geometries for the measurements of atomic emission. The XL view.
Okay, remember that I mentioned just now on how the emission spectra is viewed. Yeah? You can use axial view
And the radial view.
Okay.
The XL view offers a lower detection limit, while the radial view has a better stability and higher precision. So which one shall we use? In this experiment, we'll be using the XL viewing geometry, since we're interested in trace analysis of heavy metals in water sample. A lower detection limit may be more suitable for our case. If we are dealing with sample with higher TDS concentration, a radial viewing geometry may be selected. By the way, the plasma generated is quite beautiful. Feel free to take a picture of the plasma in the lab.
Okay, so these are steps involving, these are the atomization and the excitation of a process of using inductively coupled plasma, how plasma is generated. And the next part is the experimental part. So the experimental design, just 5 minutes, yeah? 5 minutes more.
Hey guys, welcome back. In the previous videos, we have learned how ICP and AES work. The next question will be, what is this experiment about? In this video, we will take a closer look at the experimental design. In this experiment, we will learn how to, and we will use multi-element standard to perform external calibration and to spike our sample to investigate if the metric interference is within the acceptable range. In the lab, you will have a chance to learn how to set up the autosampler, and we will show you how the different parts of the ICP instruments look like. You will also have hands-on experience operating the machine and see how the plasma is being generated. Finally, for the experiment is a little bit different from we may analyze 6 to 10 water samples to remove any solids from our samples. So why do we use nitric acid in this case? Why not hydrochloric acid? Let's discuss about it in the lab. At this point, you may be wondering, what if you need to perform ICP-AES analysis of a solid sample next time during your internship or at work? Solid sample cannot be introduced into the plasma directly. They have to be transferred into the plasma using electrothermal vaporization, laser ablation, or they must be made into a solution using acid digestion first. Acid digestion usually involves the dissolution of a solid sample in a hot acid. For example, if we would like to analyze soil samples, we will need to dry the sample and grind them into smaller particles, and even higher extraction temperature. This method enables us to effectively extract most elements from the soil sample. Finally, we need to remove any remaining solids using gravity filtration and a stream filter to prevent clogging the sample introduction system in ICP. So this is how the sample preparation looks like. Drying and grinding the sample to reduce the particle size, microwave digestion with hot acid to extract the elements from the soil sample, filtering off any remaining solid to prevent clogging the sample introduction system. This diagram here shows an atomic emission spectrum of a Martian rock obtained from the rover Curiosity. As we can see here, each element has a set of characteristic emission wavelength, as indicated on the x-axis. And on the y-axis, we have the counts, which represent the emission intensity. Then the next question would be, how do we determine the concentration of each element present in our sample from the emission intensity of their characteristic line spectra? In other words, how do we perform quantitative analysis using ICP-AES? Well, the answer is through an external calibration, which most of us are already familiar.
Okay, so we discussed this last lecture, that you have to provide standard curve first. You have to construct a calibration curve by providing standard solution first to the system. Okay, so this is called external calibration.
In this experiment, we'll be using multi-element standards containing these 13 elements of interest. Based on the ICP-AES results of the multi-element standards, we can plot calibration curve with emission intensity on the y-axis against the concentration of the multi-element standards on the x-axis. For example, in this case of silver, if the emission intensity obtained at 328 nanometer is 4,000 units, using the calibration curve, we can back calculate the concentration of silver present in the unknown sample. In this experiment,
so this is a manual way of calculating the concentration. Of course, this you don't have to do this. The software will auto calculate everything, okay? But of course, you have to construct this properly by using from the salt from scratch, where you have to measure the salts and do the solution first. But of course, you can use the commercial internal standards, just like he mentioned before, that they use the multi-element internal standards. So these standards you have to buy. Okay, we have to buy if you want to do mix a few elements at one time. So it's difficult if you want to prepare your own standard solution if it is a mixed elements as a multi-element sample. So you have to use multi-element internal standards. So I think that's it. What we're going to do is to stop here first. Okay. All right. Why is it stop sharing? We're going to have a break